Inside every modern artificial intelligence tool, the logic relies on microscopic silicon circuits. But to make those tiny circuits function at scale, tech companies are building some of the largest, most sprawling structures on Earth. Entire rural landscapes in places like Virginia and Indiana are being overtaken by what some call silicon cathedrals. These are windowless, industrial-scale data centers dropped right next door to quiet residential neighborhoods. To keep up with AI's intense processing requirements, tech giants are racing to construct these facilities at breakneck speed. By 2026, companies like Amazon, Microsoft, and Meta are projected to spend a combined $650 billion on new data center infrastructure. This chart shows the projected energy needs of AI compared to the baseline power usage of entire nations. From the launch of ChatGPT to next year, AI compute is expected to add up to 50 gigawatts of global power demand. That is roughly the equivalent of the total yearly electricity usage of France or Germany. We often think of algorithms as pure software, floating cleanly in the cloud. But code cannot run without physical energy. To push the boundaries of machine learning, the global economy is now completely bound by the hard limits of concrete, steel, and high-voltage power lines. To train smarter AI models, manufacturers must pack more logic gates into the exact same physical space. At the same time, the buildings housing those chips must become exponentially more robust to handle the strain. Two distinct companies sit at the far ends of this physical spectrum. On the microscopic side is ASML, engineering the tools that make ultra-dense chips possible. On the macroscopic side is NVIDIA, building the industrial infrastructure to keep those chips alive. When you pack billions of calculations into an area the size of your thumbnail, you generate extreme friction and heat. Advancing semiconductor manufacturing creates a thermodynamic problem that can only be solved by industrial-scale hardware. The origin of this heat problem starts in the Netherlands with a company called ASML. They hold a strict global monopoly on a technology known as extreme ultraviolet, or EUV, lithography. Lithography uses light to print microscopic circuit patterns onto silicon. ASML's EUV systems achieve this using extremely short wavelengths of light, measuring just 13.5 nanometers, bounced off some of the most precisely polished mirrors on Earth. To manipulate light at that precise scale requires a machine weighing over 180 tons and costing upwards of $200 million. Chipmakers like TSMC rely completely on this equipment. It is the only commercially viable way to print billions of transistors onto a single processor. ASML's ability to drastically shrink transistor size provided the physical density required for modern machine learning. Their engineering is the primary catalyst for the current artificial intelligence boom. The direct output of this intense manufacturing process is the completed wafer. Each small square will eventually be sliced into an individual ultra-dense chip. But density comes with a strict physical cost. Running these processors continuously at near maximum load means the silicon produces massive amounts of waste heat. Standard data centers rely on massive fans to blow cold air over the servers. However, air is a terrible conductor of heat. Once you pack enough advanced GPUs into a single rack, blowing air over them is no longer enough to prevent the hardware from melting. To actually utilize the chips ASML helps create, the entire life support system of the data center has to be ripped out and rebuilt from scratch. This is where NVIDIA enters the equation. They manufacture the physical armor and liquid cooling networks that keep these high-density servers from melting. Inside the server floor, the white space, NVIDIA deploys coolant distribution units. These systems pump specialized fluids directly to the hottest components, absorbing heat faster than air. Cooling is only half the battle. Outside the server floor, in the gray space, modern AI campuses are drawing over 1 gigawatt of electricity. That is enough power to run a small city, concentrated into a single commercial plot. Managing that raw electricity requires massive high-voltage utility transformers. NVIDIA engineers the power connections and control buildings that tie these components into the data center. You can design the most sophisticated chip in human history, but without heavy industrial cooling and strict electrical protection, that chip is just a very expensive fire hazard. The modern AI supply chain relies on a delicate balance. ASML engineers the theoretical computing potential, while nVent builds the physical reality that allows that potential to operate. This ecosystem covers an extreme physical spectrum. It starts with manipulating 13.5 nanometer light beams and ends with managing gigawatts of heavy electrical flow. Every query, every generative image, and every automated decision in the global economy requires these two distinct disciplines to function in perfect harmony. And this physical tension is only going to scale. The next major frontier of processing power lies in quantum computing. To process information at the quantum level, these specialized computers require an even more precise manufacturing environment than today's silicon wafers. Because quantum states are incredibly fragile, any slight fluctuation in temperature or electrical current will immediately destroy the calculation. They require absolute thermal isolation and zero-fail power grids to maintain stability. Human technological progress is now dictated by physical limits. The future of computing depends on the mastery of extreme physics, from microscopic light to industrial-scale power grids.